Hello, everyone. My name is Giulia, and I am based at Birkbeck College. And today I'm going to tell you about basic concepts of Fourier analysis. This lecture is going to be very, very basic. I have put it together thinking of people like me with a background in biology who don't have really much maths and physics beyond high school level, who would like to understand the theory behind image processing. And we use Fourier analysis in image processing all the time. And this is just a by no means comprehensive list of steps where we use Fourier transforms, for example, high and low pass filtering, the noising, anytime we deal with the CTF, when we calculate cross correlations, convolutions, when we look at the power spectrum of images, when we want to resample the data, determine the symmetry, in tomography, when we deal with anisotropy in general and this missing wedge in particular for tomography, when we want to assess the resolution of our map, we look at the Fourier shell correlation and other post-processing steps and much more than that. So in this lecture, I will give a brief, very basic overview of what Fourier transforms are, and then show you some examples on where we use them in image processing. Okay, so let's start with this very, very basic concept, which is that any function can be expressed as the sum of sine waves. Now, for example, this is a one-dimensional function that can be expressed as the sum of these two basic sine waves. Here we have another function which looks more irregular, which is the sum of 3, and so on and so forth. We can have a much higher number here. An image can be considered as a two-dimensional function. So we have certain gray value or intensity values as a function of the coordinates, the XY coordinates. And so in the same way, an image can be expressed as the sum of two-dimensional sinusoidal waves, like here. So this is just to show you how you can imagine these sine waves, so the intensity or the brightness as a function of the coordinates. So here I want to show you a movie that I made to illustrate how even very complex images are can be expressed as the sum of sine waves by doing it the other way around. So here on the left side of the movie, you will see each sine component being added. And on the right side, you will see the cumulative sum, so the image that is being formed. So here you can see we start with sine waves that are getting faster and faster oscillations, and they're going in different directions. And we're just summing all of the images of these individual sine waves here on the right. And you can see that shape starts to appear, which as you start adding faster and faster oscillating sine waves here, you can see finer and finer details of the image, which is clearly a portrait, and where you can distinguish the eyes, the nose, the mouth, etc., etc. And that's actually the portrait of Fourier. And to quote from Fourier, the profound study of nature is the most fertile source of mathematical discoveries, which is very true because we actually encounter Fourier transformations or Fourier decomposition in nature. And this is just a couple of examples with which you will be very familiar. So for example, when we hear a sound, this comes to our ears as an ensemble of many, many different frequencies, many, many different waves with different frequencies. And inside the cochlea, the sound is decomposed into the basic frequencies because at different points along the cochlea, cells will have receptors that get excited by a particular frequency. So essentially what happens is that each group of cells will react only to one frequency and send a message which only brings the information about that particular frequency. And then all of these frequencies are put together again somehow in our brain. Same concept for the rainbow. You know that the white light is made by many different colors all put together. So we have different wavelengths of different frequencies all combined, and then we can divide them by passing the white light through a prism. You're all very familiar with this. Okay, so how can we then describe the sine waves that compose our function of interest, our image, our sound, whatever it's going to be? We have three parameters to describe a sine wave. One is the period or wavelength. So this is how long is one cycle. Okay, so how often does the oscillation repeat identical to itself? So in the case of images, these are space units like meters or Armstrong or nanometers. In the case of or pixels. Okay, so the wavelength or period is the inverse of the frequency. So a wave that oscillates slow will have a long period or a long wavelength, and will have a short frequency. So the other parameter that we are interested in is the amplitude of the sine waves. So this is quite intuitively is the maximum value of the sine function. Okay, and in case of images, is the gray value or the brightness of the image. So that is quite intuitive. And then the third parameter is the phase. So the phase defines how much the wave we are interested in this case, the blue wave, is shifted with respect to a wave that starts at 0. So if this can be defined as an angle. So if you imagine that you have a point that is going around a circle, and we consider the projection of this point along the y-axis, for example, we can plot the position along y of the projection of P, as P is going around in the circle, and this position of the projection will form a sinusoidal function. Now you can see here that depending on the starting position of P, we start off with a different value of y, and that defines the phase of the sinusoidal function. So in this sense, we can define it as an angle. Okay, so this representation of sine waves will be very useful in other contexts, but I'm not going to delve into this at all, just to explain why we express the phase in angle. So all of these you should be familiar with really, but it's just mainly a reminder. Okay, so we said that every function can be expressed as the sum of sine waves, and each sine wave has a certain frequency, a certain amplitude, and a certain phase. So now we can go on to the next step and say that we can describe each function by defining these parameters of the component sinusoidal waves, and in particular by defining the amplitude and the phases as a function of the spatial frequency of the sinusoidal components. Okay, so for any given frequency, there's going to be one sinusoidal component which is with a certain amplitude and phase that we can add to form the image, like I showed you with the image of Fourier before. For example, here we have again our one-dimensional function, which is made by the sum of these three basic sine components. And each one of these three is a certain frequency, a certain amplitude, and a certain phase. So now if we take a plot where we have the frequency on the x-axis and we plot the amplitudes on the y-axis, we can say that we have 0 amplitude everywhere, but frequency 2, suddenly we find that the amplitude is 2. So there actually is a positive component there that contributes to the wave. So we have this dot here in the plot. We have another one at 5 and another one at 10. We can do the same with the phases. Okay, so again, we plot along the frequency domain. We plot the phase information of these waves. And we have that for frequency 2, the phase of the corresponding wave is is -50, 0, and 40, etc. Okay, so basically these two plots together convey exactly the same information that is in the original function. Okay, we can go back and forth from one to the other. They say exactly the same thing. Okay, we can actually put together the phases and the amplitudes into one single plot, if you wish, or one single number. We need to make a complex number that contains both information about the amplitude and the phase. So this is the form that the complex number takes. I'm not going to go into the details of how this can be derived. But if you're familiar with the Euler representation of complex numbers, you will work it out pretty quickly. So basically what we can do then is we can represent any function, okay, as this complex number as a function of the frequency of the sine components. And this representation is the Fourier transform of the function. Okay, so the Fourier transform is nothing else than the representation of the amplitude and phases of all the component frequencies of the function. Okay, so actually when we represent a Fourier transform, well, if you look at a Fourier transform, for example, when you look at, you want to see the contrast transfer function of your image, for example, etc. For representation purposes, we use the intensity of this number, which corresponds to the square amplitude. So we can't represent, either we represent the amplitudes or the phase information, because we can't represent a complex number. And usually we represent the squared amplitudes. That's what we call a power spectrum. Right. So one important property that I want to mention now is that the intensities or square amplitudes of a Fourier transform of the power spectrum is always centrosymmetric. Okay, you can imagine that if you have a wave going from left to right, then you have the same wave going also from right to left. So there's going to be a point in the Fourier transform identical in intensity, also going in the opposite direction. This is also true for images. And this is why when you have the Fourier transform of an image, the point with frequency 0 is in the middle of the image, okay? Right, so let's go back now to our very simple image, which is the sum of these three sinusoidal components, okay, which we can also represent like this. So each one of these sinusoidal components has a Fourier transform, which is nothing else than a peak corresponding to the frequency of these one oscillating wave. So in this case, we also have a directionality. So in the case of this blue one here, the peaks are going to be along the direction of the oscillations from the center. They're going to be at a certain distance from the center, which depends on the frequency. So the closer they are to the center, the lower the frequency. And they're going to have a certain intensity which corresponds to the amplitude of the sine function. So here we have a sine wave that is oscillating slower, so it's got a longer wavelength, or a smaller frequency. So you can see that here the peaks are closer to the center than there, and this is even slower. So these peaks are even closer to the center. Okay, so when we put together these three components, or the three transforms, then we get the Fourier transform of our original images, which will contain 6 peaks of different intensities in different directions and at different distances from the center of the Fourier transform. Okay, and if we look at it in a usual representation, when we look at a power spectrum, it will look like that. Okay. Okay, good. So as I said, we have in the middle of the Fourier transform, we have the 0 frequency components, and then the frequency increases as we go away from the center of the Fourier transform. So close to the edge of a calculated Fourier transform, we will find the information about the high frequency waves, and close to the center of the Fourier transform box, we will find information about the low frequency components, so the slower oscillating components of our image. I will come back to that many times during the lecture. One important property of Fourier transforms is the Fourier inversion theorem. So this states that the Fourier transform of a Fourier transform of a function recovers the original function. So this basically means that I can transform this zebra and then obtain a transform, and I can transform this transform and I obtain the zebra. This is very, very important because, as you would probably know already, in image processing, we keep switching back and forth from what we call real space to what we call reciprocal space or Fourier space. And we need to perform different operations in the two different spaces continuously. So this property is very important for us to be able to keep going back and forth. For example, we may want to mask our object in real space, but filter it in Fourier space. Okay, so what happens if we sum two images? That operation is equivalent to summing the Fourier transform. This is quite obvious given the fact that we are talking about a sum of the sine components as being the Fourier transform. So that's quite intuitive. That same is not true when we are multiplying images. So if we are multiplying two images, we are not multiplying the two Fourier transforms. We are doing another operation on the Fourier transform, which is called convolution. So I will explain what this means, and you will hear a lot more about convolution in the second lecture of this day from Elena Orlova. So, and by the way, the same is true if you are convoluting two images, that should be image 2, then you are multiplying their Fourier transforms. What is convolution? So let's imagine that these are my two images or two functions that I want to convolute with each other. And as I said, this will be explained to you in a lot more details with formulas and everything in the next lecture. When we're convoluting these two images, essentially we are sort of placing this image here at every pixel of this other image. So we're doing a multiplication of this image with every pixel of the first image. Okay, so that's what convolution is essentially, and this corresponds to a multiplication of the Fourier transform. Now, you will see during the whole course that the convolution is something that happens quite often in Cryo-EM that we need to take care of. We need to either deconvolute things or convolute things, and these are very difficult operations to perform in real space, as you can imagine. Whereas in Fourier space, we're just talking about simple multiplications or divisions, which are obviously very easy to perform. So yeah, this is just a zoom in to show you how the result of that convolution, where that kind of replay function has been applied or multiplied to every pixel of the original function here. Okay, so I showed you so far how we can express a function as the sum of the sign components. And I showed you some examples where we had like 2 or 3 sign components, or some number of sign components adding up to form an image. Now, when we are doing electron microscopy, we are dealing with digital images, of course. And so the image function is not a smooth function, is a discrete function. So every pixel will have a jump in gray value to the next one. Okay, so it can actually be shown that in order to represent a discrete function, we need an infinite amount of sinusoidal components or Fourier components. Okay, so this can be intuitively understood here from this slide, which I actually stole from Peter Rosenthal, where you can see that if this is your function, this is a hot function, it's a discrete function. You can approximate it decently well with a sine function, but you can do better if you sum 2 sine functions, and even better if you sum 3 and 4, etc. Okay, so eventually when you've summed an infinite amount of sine function, you have your hot function back. Okay, so that means that there's an infinite amount of Fourier components. What this means in terms of what happens to the power spectrum of images, of digital images, is that whereas the power spectrum of an image which would be smooth, so not digitized, would look like this. So here we have, it's the same I showed you in my introductory slides. When we are dealing with digital images, the power spectrum would look like this. So we have the sinusoidal components with period n and half and a third and a fourth, etc. Okay, so when you actually will look at images of periodical samples, like a crystal or something, you would see something like that rather than like this. Okay, so this is why. Okay, another important thing to mention here is the Nyquist limit. I'm sure you've all heard of the term the Nyquist frequency, or and it can be explained looking at the properties of digital images. So if we have an image, here I am showing a pixelated image where every pixel is either black or white. Okay, so these are the possible positions where we can put the values of our function. So you can see here that if our function oscillates faster than every 2 pixels, so if the period, which is defined here by the red line, is smaller than 2 pixels, then we can't really represent this function into this pixel grid. Okay, everything becomes muddled up. This is actually true also, you know, if they're not multiple of these, but that doesn't matter. We are looking at the smallest, the highest possible frequency, or the smallest possible oscillations that we can represent on a digital grid is of twice the pixel size. Okay. So that means that we cannot, if we have a certain pixel size in our image, we cannot represent any sinusoidal components that oscillates faster than that. So that essentially sets the resolution limit of our image, the theoretical resolution limit of our image. Okay. And if we take then our image and calculate the Fourier transform, you will remember I told you that the low frequency or the 0 frequency component is in the middle of the image. and the high frequency components are at the edge of the image. Now, because we know that the highest possible frequency components is 1/2 pixel, then we can attribute the last pixel of the Fourier transform, the one that is half a box size away from the center, to the frequency 1/2 pixels. Okay, that's what we call the Nyquist frequency. That's the resolution limit. You can't go any further than that. Okay, so you can understand the Nyquist limits in real space like this, or in Fourier space like this. And knowing where the Nyquist limit is also important because it allows us to really understand the formula that we use to relate real and reciprocal space. Now, I want to take some time to explain this to you because you will need to use this a lot. Now, I have to say that modern software is great and it allows you to get to the end of your reconstruction without really doing this. I mean, this is quite new. But for example, there are certain software, a lot of the subtomogram averaging software, which is not as advanced and user-friendly as the single particle one, for example, will require to know this formula. And I think it's good to understand how things are calculated inside the black boxes. So imagine, so you have a certain box size, okay, which is going to be the same for your image and your Fourier transform. Then you have a certain pixel size, okay, this is defined in real space, so how many angstrom per pixel you're representing in each pixel. And this formula relates any position in your Fourier transform, so a distance from the center of your Fourier transform to the resolution that is represented at that particular radius, okay? So the alpha box size, which is the length of this blue horizontal blue arrow here, is to the particular radius that you want to inquire about here, R, like 1/2 the pixel size, which is the Nyquist frequency, is to the 1/2 the resolution, okay? So in some cases, for example, we will see some example, you may have a Fourier transform and you may see that you have some peaks of intensity at a certain distance from the center, and you would like to know what distance in real space that corresponds to, because that means that you have a repeating feature that has that particular distance in real space. Then you know R and you can work out the resolution. Or you could do the opposite. You have a map and you would like to filter it. We will see that later. And you know that you want to filter at a certain resolution. How do you calculate the radius of your filter in Fourier space using this formula? I'll go into this in more detail in the next few slides. So this is an example of images of repeating units. So this is a 2D crystals, and these are microtubules, which are like have a helical arrangement, and you can see the spots. So from the distance of these spots to the center, you can work out using the formula I showed you how often, what is the real space of the repeats. Filters. Okay, let's get back to this very simple image, which is the sum of these three functions here. So this is a high frequency component, so it will bring about high resolution information, and the information is going to be close to the edge of the box or further away from the center anyway, etc. Okay, so, and then we have the Fourier transform of the image is going to be the combination of these three components. Now, let's say that I want to eliminate the high frequency components of the image. in this case, it's only 3 components and the high frequency isn't going in only one direction, so I could simply subtract this. But let's assume that I have many more components and there are many, many high frequency waves that are going all sorts of directions that I want to eliminate. The faster way to do this is to take the Fourier transform, apply a mask onto it, and delete all of the information that is beyond a certain radius, calculated as I showed you before, and then back transform this to obtain an image which doesn't have the high frequency component anymore. This is called a low pass filter. We can do the other way around. We may want to get rid of the low frequency components of the image. In this case, we apply a mask that removes anything that is close to the center of the Fourier transform, and we obtain an image where we have removed the low frequency components. Now, let's look at some, this is called a high pass filter. You can put them together at the same time using a band pass filter. So you let through things in between two frequencies. Right, so let's look at an example of low pass filtering to see what it actually does to our images. So here we have again Fourier with its Fourier transform, and we can low pass filter Fourier by applying a mask and remove everything that is outside a certain radius of its Fourier transform. So in this case here, we have an image which is 50 centimeters big and made by 750 pixels. So we can use the formula I showed you before. We have the pixel, we can calculate the pixel size from here, and we can then calculate the radius that we want to use for the mask so that we eliminate everything that oscillates faster than 2 centimeters. Okay, so this radius turns out to be 25 pixels. We apply that and then we back transform, and now we have a Fourier where all of the features finer than 2 centimeters, for example, you can see all the lines here, the hair, etc., are not visible anymore. They're not there. Okay, we can be even tougher and decide to eliminate everything that is finer than 10 centimeters. And now you can see that we're starting to really blur Fourier's face here. So why do we use low pass filtering in Cryo-EM? There are a number of reasons, and one of the main ones is that in Cryo-EM images, as you will learn in the next set of lectures on the image formation, the signal to noise ratio decreases with spatial frequencies. So as we go to higher spatial frequencies, the signal decreases. Okay, that means that there is a lot of noise. And when we are trying to interpret our images at many different steps, we may want to remove that noise. For example, if we have to pick particles, we may want to remove all of the high frequency information, which is useful later on, but it also contains noise. So we low pass filter for picking, for example. Likewise, if we want to use a reference for alignment, we want to make sure that there is no high frequency noise in that reference, because that can bias our alignments. And again, you go into this quite a lot. And so we need to low pass filter the reference. And as I said before, with single particle software, all the ones that I know that is used these days, you give the value of the filter in Armstrong or in nanometers. You don't have to do this calculation yourself, but you do for some subtomogram averaging software or some older software that some people may still like to use. Okay, high pass filtering, I'll skip how we calculate the radius, is the same as before. Let's look at this sort of extreme example down here where we have eliminated all of the sine components to this image function that oscillates slower than 2 centimeters this time. So now you can see that we can see all of the very fine details, but we lost the overall black and white oscillations. Okay, so you can see here, for example, that you have the black coat and the white shirt, and that kind of information would be carried by a very slow wave, right? Because you have a peak and then it's going to be going negative here. So that's almost as big as the box size. So that would be represented very, very close to the center. And when I eliminate that, I lose the black and white pattern between the coat and the shirt. Okay. Okay, so yeah, this is just another couple of fun facts about Fourier transforms. So if we have a Fourier transform of two images that are shifted with respect to each other, when we look at the power spectrum, it actually looks identical, okay? But the phases are different though, okay? So if you think about what the phase means in terms of where does the sine wave starts compared to a reference sine wave, then you will understand why the phases are different, but then the amplitudes are the same. Here, when you rotate an image, you also rotate its Fourier transform. Might be interesting to note here that here we have an image with 5 points, and the Fourier transform has got 10, and this is because Fourier transforms are center-symmetric, so the 5 points are all in the same half of the Fourier transform, and there's another 5 in the other half. Okay, so that's something to remember and take into account when you look at symmetric particles, for example, in Fourier space. Okay, what happens if we invert the phase of the Fourier transform? Now we have our Fourier, we have the Fourier transform, and now we take all the phases, okay, and invert them. So subtract or add 180 degrees to the value of the phase. Now, if we can think about each one of these components as a kind of simple sine wave, like here, when we add or subtract 180 degrees, what we are doing is we're shifting it by half a period, okay? And essentially what we're doing is making everything that is white becomes black and everything that is black becomes white, okay? So that's what happens when we invert the phases. Again, you will not probably see these very often, but one must take into account when the phase inversion, when doing, for example, CTF correction, this can happen, and it's important that the particles always have the same color with respect to the background. Are phases or amplitudes more important for an image? Now, here we have two different images. We're taking the two Fourier transforms, and then we are making a hybrid transform where we take the phases from this image here of Fourier and the amplitudes from the zebra. And what we obtain is something that looks like Fourier much more than it looks like the zebra. So this means that the phases are more important. And this is because the phases define where for a certain frequency of oscillations, where is the white and where is the black, rather than how white is the white and how black is the black, okay? Likewise, if we do the opposite, we obtain something that looks more like the zebra than Fourier, okay? Good. So that, you know, it might ring a bell to some of you who may have experience in X-ray crystallography and know that determining the phases accurately is very important, that's a big advantage that we have in Cryo-EM, as I'll come back to later. Okay, so I've told you a lot about 1D Fourier transforms, like the basics and some kind of properties and things, 2D Fourier transforms and how they apply to images. 3D functions have 3D Fourier transforms. It's just exactly the same, they're just harder to represent. So if we have a reconstruction, that's nothing else that's a function of x, y, z. So we have an electron potential as a function of x, y, z. Okay, so for example, this is a map of a protein, and this is its Fourier transform. Okay, again, the low resolution information is close to the center of the cubic box, and the high resolution information is close to the edges. And here we have another map, and this time is a helical assembly. I can't remember what it is. And this is its Fourier transform, where you can see the repeating pattern along the axis of the helix. Okay, so introducing 3D Fourier transform means that we need to introduce the projection theorem. This is a fundamental theorem that we use when calculating three-dimensional reconstructions from two-dimensional projections. So what this theorem states is that if we have an object and we collect two-dimensional projections of the object, now let me just specify, projections means the summation of all the density throughout the object along a particular direction. So when the electrons are going through this object, they form an image which is the sum of the information that they encounter at every plane throughout the object, like if it was light going through a glass. Okay, this is important to remember. So if we have an object, we can have the projections, which in fact is what the Cryo-EM images are. We can calculate the two-dimensional Fourier transforms of these projections, and then we can intersect them all at where the frequency is 0 for all of them. So they all should have the same value at that particular frequency, because it's 0 and it's the same object. So we can intersect them all in the orientation that they were collected at. And if we then consider this as a 3D Fourier transform, when we do a back transform, we obtain our object back. Now, of course, I'm only showing 3 planes here for convenience, but this is true when we have an infinite amount of planes that can fill the Fourier space, and you'll see what happens if that doesn't, if that is not true a bit later. So, and kind of understanding the projection theorem allows us to understand also some other aspects of the reconstruction. For example, we can discuss about what are weighted back projections. So I'm sure that all of you have heard about the term weighted back projection. So we will calculate a reconstruction from 2D projection images in 3D. We don't simply do a back projection, we do a weighted back projection. Now, this is a very, very common term in tomography, but it's the same for single particle as well. And you can imagine doing the 3D reconstruction by back projection, as if you take each projection and you smear it back in 3D to form your object in the middle. Okay, but you can also think about calculating the Fourier transform and intersecting them in 3D. And this way of thinking, it's easier to understand the weighted back projection. So because we are dealing with digital images, okay, when we intersect all of these Fourier transforms in 3D, they're going to be 1 pixel thick, okay, which means that they will carry the information in the center many, many more times that they will carry information close to the edge of the Fourier transform. So the information that is at low frequency, close to the center, will be up-weighted with respect to the high frequency information. Okay, and in fact, if I simply do a back projection of this image, this is Helen Sable here, I obtain this. Okay, so the high resolution information here is there. Okay, so I simply projected this image and back projected it. Okay, nothing has gone lost. But the high resolution information, we can hardly see it because it's overwhelmed by the overweighted low resolution information. So we need to wait for this to obtain a back projection where all the frequency components have a fair representation. Okay, so that is what is weighted back projection. It doesn't have to be applied in Fourier space. It can be done in real space, but it's better understood in Fourier space, I think. The projection theorem also allows us to understand anisotropy. So what if we do not have projections from all angles, right? So I had 3 in my example from the projection theorem, which of course is a bit extreme. We might have millions of projections from millions of particles, but what happens if some views are missing, okay? So we have what we say incomplete Fourier sampling. Okay, so this is how, you know, I'm sure just showing a 2D slice here, but this is how a Fourier transform will look like if I'm intersecting the Fourier transform of projections that have preferential orientation, or in this case, it's the one of tomography. I have a missing wedge of information because I cannot tilt the sample all the way through. So I'm missing some views, I'm missing some projections, okay? This means that the reconstruction will be anisotropic, okay? So in the case of tomography, for example, you can see this is the reason why I chose this picture of Helen, is that she has a very nice shirt with vertical stripes and nearly horizontal stripes. And you can see that in an anisotropic reconstruction where I'm missing the information along the vertical direction here, I don't have projections along these vertical directions, then I'm losing the information about the horizontal stripes. You see, those have disappeared, while the vertical stripes I can still see very well. Okay, so this is what happens when you have an anisotropic reconstruction. You basically, that's where your streakiness comes from. You know, you might be familiar with your reconstruction becoming like all elongated and streaky. That's the same thing that is happening to Helen's nose here. Okay, so another thing I want to mention is the, which is very well understood in Fourier space, is the Crowther criterion, which is a, it can be used as a measurement of resolution given a certain number of a certain sampling of Fourier space. Let me rephrase this. When we do a reconstruction from projections, we have the projections sampled from each other in a certain way. And if the sampling is not fine enough, okay, then we will have, after a certain resolution, which is here roughly indicated by this dotted circle here, we don't have full information. So unless we're doing more averaging with more projections here that can fill the spaces in between, our resolution is limited to where the radius here indicates. Again, we can use the usual formula to know what resolution these are is. And this Crowther criterion is important in tomography because it allows us, for a given tilt increment and a given tilt range, it allows us to know from one individual tomogram what's the maximum resolution we can possibly achieve. And it's also important in single particle because it allows us to decide what the angular sampling should be for a reconstruction if we want to achieve a certain resolution. So here is the formula for that. It's really very basic geometry, so you can take some time to look at this. But just to say, this is not just theory, and this is what is applied, for example, within Relion. I'm sure a lot of you have run Relion jobs, and you know that in the 3D auto refine, it tells you at every iteration, this is your resolution, which requires orientation sampling of whatever degrees for a particle with this size. And this is exactly how that number is calculated. Okay. Okay. So basically, this is the end of the part where I wanted to give you some basics about Fourier transform and how we use them, I would like to spend a few minutes here to kind of relate diffraction and Fourier transforms. Okay, because I think it is important to know that when you are looking at the Fourier transform of your images that you obtain from the microscope, you're not looking at something that is unrelated to the microscope. You're actually looking at something that physically exists in the microscope. And that will help you understand where the contrast transfer function is coming from. You will have a whole lecture about the contrast transfer function, but I think understanding this at the beginning will set you with the right mind to understand that. All right, so we have a object, an atom, okay, and then we have a wave, an electron wave coming to it. You will get, again, much more details on what happens when these two interact in the next set of lectures, but oversimplifying here. This wave can just go through undisturbed, or it can be scattered, okay? And then this scattered wave will be going towards the objective lens, which will focus it to form the image at the level of the detector, okay? So now let's assume we have multiple atoms, okay? Again, we have an incoming wave, and we can have a wave that is unscattered, which, if it doesn't really interact with the sample, will not have any phase shifts, and it will be, all of these unscattered waves will be in phase with each other. But then we will also have some scattered waves. Now, let's imagine we have waves scattered at a certain angle here. Given a certain distance between these objects, at a certain angle, these waves will not be in phase with each other. So that means that any wave scattered at this angle theta will not carry any information about objects that have this distance from each other, okay? Same for this angle. But now we found an angle theta, which is larger, where objects that have this particular distance actually scattered with constructive interference. So if we now look at the diffraction pattern at the diffracted waves at this particular angle, the information we see there comes from objects that were at a certain distance from each other. Okay, now we can take objects that are closer to each other, and we can repeat the same reasoning, and we find that this time, if we use this same angle theta, there's no information going through, okay? So objects at this particular distance, they don't give any signal at this particular angle of scattering, but we need a much higher angle of scattering from objects that are closer together to obtain constructive interference. Now, the relationship between the distance between these objects and the angle of constructing interference for certain wavelength is very well known. It's called the Bragg's law. So I'm not even gonna give the formula. I'm sure that all of you who have crystallography background will be much more familiar with it than I am. But this is just an intuitive representation of the Bragg's law, okay? And the only reason why I'm showing you that is because then you can understand the analogy between diffraction and Fourier transformation. So we have objects that are many distances from each other. It doesn't have to be a crystal, it can be any object. And we know that the information about atoms that are very close to each other will be scattered at a high angle, whereas the information between atoms that are far from each other will be scattered at low angles. Likewise, in a Fourier transform, we have the information about features that are close to each other. Okay, these are fast sinusoidal waves. They will be represented far from the center of the Fourier transform, whereas the information, the low frequency information from relating to objects that are far from each other, is going to be transmitted close to the center of the Fourier transform. Okay, so as a matter of fact, the diffraction, what happens in the diffraction plane in the microscope is a Fourier transformation of the object. So when we calculate the Fourier transform of our image, we're basically going backwards in the microscope and kind of seeing what was going on at the diffraction plane. Okay, it would be easier for you to understand after Chris and Dan's lectures, who will go into the microscopy more. Okay, so that's the end. I have a few homework slides, or rather things to think about, and for you to work out to see whether you understood things, and also as a initial point for discussion when we have our Q&A session during the course. Of course, you're very welcome to come up with any other questions, either during the Q&A or before that. We will provide a means to do that. But these are just some ideas. So the first one is to match the image with its Fourier transform. So you can kind of pause now and work it out, and let's see what you can do. Another thing that is actually very useful, and I think that it might be a good challenge for you to see that you can do this, is to resample your map. Okay, so imagine that you have a map that you downloaded from the EMBO with a certain pixel size, 1.7 angstrom per pixel. And that's in a box, which is 128 cubic pixel boxes. Now, your own data was collected at 1.3 angstrom per pixel, and you have boxes of 160 pixels, okay? Now, you want to use the map from the EMBO as a starting model for your data. So you need a map that has a pixel size of 1.3 and is in a box of 160, okay? So how do you resample your map? Now, I know you can all do it with rely on or kind of equivalent modern software that will do it for you. But can you work out using Fourier transforms, thinking about Nyquist frequency and its relation with the pixel size, thinking about the formula I shared with you earlier on? Can you work out how to resample your map? And another thing for you to think about, which actually has some relevance, even though not very practical or useful ones, is this. So I made this image, and I hope that you're all sitting far enough from your screen that you can all see a little Einstein in the middle of the screen. Now, if I play this and I enlarge this image, now you can see Natasha Kinski here. So you can clearly see a woman, and you can't quite make out Einstein anymore. So my question for you is, how did I make this image? If you can think about how you would do something like that, that would be good. And the reason why this is relevant is that this is the same effect that you see when you are looking at your micrographs as thumbnails. So this is, for example, the EM2 pickers, but it's the same in any picker. When you have your micrograph all squashed in a very small, very little number of pixels, then you see ice gradients. For example, you can see all these kind of black and white oscillations, which when you zoom in your image, they totally disappear. And that's exactly the same effect of what I showed you before with the image changing. So it would be good for you to think about what's going on there. Another thing that you may want to think about, especially if you are a crystallographer by background, is what is the, especially if you're not a crystallographer, what is the phase problem? So we, as in cryo-EM, as in crystallography, we have a beam, either electrons or X-ray, going through the sample, which in the case of crystallography is crystal, producing a diffraction pattern. I've told you already what the diffraction pattern is. But from then on, in microscopy, we focus diffracted rays with lenses to obtain an image. Whereas in X-ray crystallography, we take an image at the level of the diffraction pattern. okay, which is where the Fourier transform of our object forms. So why do we have a phase problem? Try and think about that. And then I think this is the last thing, is to think about the fact, so actually this slide is quite old, and say, how do new detectors break Nyquist? These are not very new anymore, and I'm sure a lot of you don't even remember when we didn't have direct detectors, but you can use the latest generation direct detectors in super resolution mode. And one of the advertisement points of these things is that they can break the Nyquist frequency, that can go to higher resolution than the pixel size. Now, you can use these pictures here to understand how that actually works, and whether you're actually breaking Nyquist or you're simply maybe changing the pixel size. Okay, that's all. Thank you very much for your attention, and I look forward to meeting you all, even though virtually, during the course.